Okay, so any question before we start? Okay, Perceptron. Okay, so remember that you have studied linear regression and also you have studied classification. So one of the application that we can use for classification is to predict the classes of certain item, or we can use that one to identify the type of item that we have. So when we talk about prediction function, it is a function that is used to predict what is the output should be for a given input. So we will train the neural network. In this session, we are looking at specific type of neural network, which is the perceptron. Okay. In the previous lecture, also we looking at the classification. Remember that for the binary classification, you should be able to draw a linear line that can separate two classes. But if you have more than two, uh, let's say you need to have k classes, that means you need to have k minus 1 number of model to divide the item that we have. So when we try look at the linear function, if you remember, this is similar to what we have in linear regression, in which we are looking at the variable xi, also the weightage for individual x that we have, and the b will be the for linear regression will be the error. When we look at the formula in terms of classification, we are looking at the b as the bias that we can use in order to change the symbol or the signage, the sign of our particular function. So if you look at this, let me get my pen first. So this is a general function when you have more than one x. So which means that your x are from 1 up to k. So at the same time also you require the coefficient to be learned or to be estimated in order for you to draw a line. So we simplify this formula. So we will have this one because this is the weightage that we have, and this is the transpose. Because when we looking at this one, x should be your vector. Okay, so when we have the weightage, we transpose them. So basically, if your x is this one, your x is this one, and then your weightage for each x that you have will be like this. But since we want to multiply them, because we want to get the summation of the multiplication between the weightage and also the x, so we get the transpose of this. So we have in the form of this. This is your m, and this is your x. So when we multiply them, we will have a single value here. And the single value here referring to this. So if you look at the linear regression that we have studied before, this is a linear function that draw a line that trying to reduce the differences between the actual values that we have, which is the blue one, and the predicted value, which is the red one. So this is for regression. But for classification, we need to draw a line that will separate the two classes. Okay, so we learn a linear function that separate instances of different classes. instances here referring to the samples of different classes that we have. So in this example, we have two classes only. So the X is positive 1 and the red one is negative 1. So when we talk about classification or linear classification, we are talking about a linear function that divides the coordinate space into two parts. So we must be able to draw a line that separates them into two. So this is also called binary classification. Or they call it positive class, and the other one is the negative class. Okay, so this is for binary classification. Remember that in the previous lecture also, we talk about how do we convert the multi-class classification into binary class classification. Okay? So when we draw a line, um, we must indicate which part is positive and which part is negative. So for that reason, if we draw a line that fulfill this function, we are saying that if the value of this is greater than or equal to 0, then we predict the output of y to be 1. Otherwise, we will predict the value for y as minus 1. So it is just a formula that represent the line on your solution space. So B in this case is called the bias term. In the previous lecture, we defined bias term as a value that can be used in order to adjust your output depending on the actual output that you have, because we want to match the predicted output with the actual output. So the bias is used to adjust the predicted output so that it will match to the actual output. And for this one, we will use the linear threshold unit to classify an example X using the following classification rules. So depending on the output, no, the input that you have, they will multiply all the value that you have, and it will produce a sign here, positive or negative, depending on the value of your final computation. Okay, like I mentioned just now, for example, we have this linear line. Okay, so what we want to do is we want to look at whether it goes to this side or this side. We do not care about the magnitude. We do not care about how large is the amount, but we want to look at the sign of your computation. If you plug in the value for x and y, and it gives you positive, so that means they belong to this side. If you plug in the value for x1 and x2, and the value is negative, then belong to the negative class. Okay, so who created Perceptron? Perceptron was initially coined in 1958. Okay, so that is the earliest year in which they start thinking about how do we imitate human intelligence by looking at the neuron and also come up with this perceptron. So they have a news. So they use this IBM 704 and they train them to play chess. And now I think the champion of the chess is the machine that they have trained. So the main goal is to find a separating hyperplane. Hyperplane because if we have two variable, then we can say that is one line to separate the line. But if we have three variable, then we need to have a 3D. So we need to have like a piece of paper that will divide the space to separate the two classes. If we have more than three, then we cannot imagine how do we actually illustrate the solution in a 4D environment or 5D environment. So go back to basic one. We say that if the value is greater or equal to 0, then it will belong to class 1, okay, or positive class. If less than 0, then we say that they belong to negative class. Okay, so if we try to relate to the neuron, so this is your input here, and we have all the weightage here. So during the training session or the learning session, we actually looking at how do we estimate the value of W1, 2, 3, 4 to N, and then somehow the weightage that we learn here will consistently give you the right predicted output if you compare them with the actual output. So the function that we have here will be the summation of the product between xi with the weightage wi. So this is the main idea. By convention, the slope parameter are denoted by the w. So this is your slope, slope parameter. In the previous example, we use m, right? So m is similar to what we have here. This is the slope parameter. Sometimes they call it the weightage. And we use this. So by default, we have two classes, positive and negative classes. And the W is referred to the slope parameter. And this is the equation that we use to indicate that to separate between the positive class and the negative class. Okay. So this is similar to what we have in linear regression. So let's give some example. Suppose we want to predict whether a web user will click on an advertisement for refrigerator. So suppose we have this event. Okay, this event recently searched for this refrigerator repair and recently searched for refrigerator reviews and then recently bought a refrigerator and then last one is has clicked on any ad in the recent past. Okay, so this is what we want to predict. So if let's suppose that we have the weightage. So this is the estimated weightage that we have. So this is learned by the perceptron. Okay, so how do we decide what is the function of here, the prediction function here? So if only one of them is 1 or turn on, the rest is off, means not occur. So total will be -1. So since they are -1, so it means the prediction is no. I go back here. we want to predict whether a web user will click on an um, advertisement for refrigerator. So if only that person search for review, that means they will not click for the advertisement. But if they are looking at these two, search for repair and review, and then the value here will be 1. So that means this guy will click on advertisement to buy fridge. So let's try another value. Okay, let's suppose he ever clicked that before. Okay, and we look at the value here because at plus 5 we have um, minus 9 because this is the bias. Okay, so the prediction is yes because greater than 0. And let's move on to this example. Okay, so if he recently purchased a fridge, so that means this one will be minus and the prediction will be no. So when you ask me, okay, how do I get all this value? All of this value are estimated by the learning system itself based on the previous samples or instance provided by the user. Okay, so these are all the coefficient or the weightage that will be learned by the system itself. So this is just to get how do we apply um, the weightage or the coefficient that has been learned by model. Okay? So if none of them are true, that means we only have minus 9. None of them is true. Okay, so none of them will be turned on. So value will be minus 9. So prediction will be so that's how we use um, the function, the prediction function in Perceptron. So the weightage are all learned by themselves. It depends on the number of iteration, the number of epoch that you have during the initialization of the perceptron. Okay? So what actually happen when they try to estimate or learn the weightage? So the first thing that they will do is that they will initialize all the weight to 0. So meaning that all the weight that you have here will be all 0. Okay? So along the time after a few iterations, they will adjust the weight depending on the output that you predict and then match with the actual output that you have. So it will iterate through the training data for each training instance. We'll try to classify the instance. Okay, if the prediction was correct, don't do anything. Do not adjust the weightage. Okay, but if the prediction was wrong, we need to modify the weights by using the update rule. So they have this update rule in order to match with the actual output that we have. Okay, so we repeat this one many times until all the predictions are correctly predicted. So we have to look at this update rule. How do they adjust the weightage for um, each item that we have, for each variable that we have, or for each weightage that we have? Okay, let's suppose we have this. So this is our update rule. So if the classifier predicted an instant was negative, but it should have been positive. So we predict them to be negative, but it should be positive, right? So what should we do? We need to convert them into positive. So how do we convert them into positive? We have to move from negative to positive. So what we need to do is we need to add a positive number. So if the classifier predicted no. On the other hand, if the classifier predicted positive, but it should have been negative. So if we predict them to be positive, the actual one is negative. So we have to move from positive to negative to match the prediction. So how do we do this? How do we convert them? So we have this formula. Okay. So we have this formula. I think you know this one already. So this is equivalent to, for example, a plus equal to 1. So basically this is a equal to a plus. So in this case, we will update the weightage with this value. So this is the predicted value. This is the actual value. If they are the same, that means the whole thing will be 0. If your output, this is your output, this is the actual output, this is the predicted output. If they are the same, don't do anything because changes will be none, 0. But if let me give you, okay. So let's suppose the prediction is wrong. Okay. No. Okay. Let's suppose this, look at this one first. Okay. If your this is your actual, this is your actual, this is your predicted value. If your actual is positive, but your predicted is negative, so you want to move towards this one, right? Okay. So this one will become, because you want to move towards positive, so this term will become positive, because if this is positive 1 minus 1, you will get 2. Okay, so your weightage will be equal to weightage j plus 2 times this one. So meaning that you have your weightage to be positive already. But if, let's erase this. If the other way around, okay, if the actual one is negative, the predicted one is positive, so this is positive. So you will have minus 1, you get minus 2. So meaning that you move this positive to become negative. So this is the update rule that we will be using. That's how they use this one in order to update the weightage and so on. Okay. Okay, but they adjust the weightage. We also have the learning rate, because if we go to the next formula, we do have the, let me, so we have this learning rate here. This is how much you want to update the weightage that you have. So this is what we call the learning rate or the step size. So remember that in neural network, you have to set the learning rate. Too small or too big learning rate will not get you to the um, lowest um, lowest cost reduction, because you tend to skip the lowest cost. Um, when we talk about what we call it in the previous lecture, we are looking at the problem. I try to remember that one. What is that problem? Let me go back to this one. Gradient descent. So this is the learning rate that we are talking about. Too much changes of your weightage will make you skip the lowest one. For example, like this, we are trying. This is the initial weightage, but every time we make a mistake, we want to reduce it. So the changes could be big or small. But if you change too big, you may miss the lowest cost. So you may be up to here. Okay? Or if you make the changes very small, very slow for you to get to the global cost minimum. Okay, so this is the problem of gradient descent that we have. So this is the learning rate that we have. Let me go back to the previous one. So in this example, we are looking at the changes of the weightage without the learning rate. Okay, so just now we are looking at the changes of the weightage based on the learning rate. So this is the program that we have for the, what we call it? Yes.
Agree.
Sorry. Again. Again. Can you hear me?
Can doctor.
One of your friend asked about what? I didn't hear just now. Just stop me if you don't get what I'm trying to say. So this is the pseudocode on how we update the weight of the drone. So for example, like this, we are looking at the X and also the Y output. So for every iteration, we will update the weightage for the function here. Okay. So if your predicted output is equal to the actual output, then you don't do anything else, you fix it. So how do you fix that? So if this is your actual output, this is your predicted output, so they have the wrong sign here. So what happen is you will make it bigger because you want to move from negative to positive. If the other way around, you want to make it smaller, so you want to have the positive one to become negative one. So we will apply the update rule that we have here. This is our update rule. Okay. So this one will automatically adjust the weightage by themselves. So we will repeat step 3 to 5 until all of the predicted output is the same with the actual output that you have. So this is the pseudocode. And also we have the bias here. Okay, so this is the, if we are looking at the linear regression, this is the y-intersection when your x is 0, right? But in the neural network, they are used in order to balance your output or the predicted output so that it will match with the actual output that you have. Okay. Okay. For most of the problem, we can separate them linearly, but all of them can be separated linearly. So, for example, this one we cannot, and this one also cannot. Okay. So this is linear separability. If we look at the AND gate and the OR gate, they are linearly separable. So if we plot them here, then we can get the X. We can separate the X with the blue O there, a straight line. This for the AND gate. For the OR gate, we also could separate them. For the XOR gate, we need two lines, two models to classify them. So this is not linear.
So Director, we cannot see the slide.
See the slide. Ooh. Okay. Let me go back lah kan. Sini kan tuh.
Yang tadi next. Before this, di sini.
Ini kan?
Yeah.
Okay, so for this one, the next two is not linearly separable. We cannot draw a line to separate them. Okay, so in this case, we can use the need more model to separate them, like what we have in the previous lecture. So this is linearly separable. And if, for example, if we have two input and output Boolean neuron, it is possible to represent them using the AND and also the OR function. So for this one, they are separable. This is for the AND gate. Okay. This is just to show you for these two input and one output for AND function, AND gate function. We can separate them. For the OR gate function, but we cannot separate this XOR function because we need two model here to separate them. So the training instance are not linearly separable. The classifier will always get some prediction wrong. So that's why you cannot have 100% accuracy. So you need to implement some type of stopping criteria for when the algorithm will stop making updates. Otherwise, you will go to infinite loop. Okay, because if you look at the pseudocode here, you repeat step 3 to 5 until what? This is your all your predicted output is the same with the actual output that you have. So if this is never met, means if your accuracy is not 100%, you will go to infinite loop. So that's why they said in this example, this problem, this is not linearly separable. So we need to have some kind of stopping criteria. Okay, so if you adjust many times and you still cannot get that one to be correctly classified, then you will stop it. So you usually you specify the number of iteration, the number of epochs. So that's the reason why we limit the number of epochs. So some of the problem you can solve using small number of iteration or small number of epochs. Some require higher, and it doesn't mean that if you put higher number of epochs, you will get higher accuracy or you get 100% accuracy. Okay, so this is the learning rate. Okay, this is just to show you the illustration of the Perceptron work. So on the left side is the training, and the test is the right side is the testing phase. So the green light that you see is they are trying to test whether they got the right prediction by looking at which side they belong to. So they will move the line that will separate these two classes. Okay, so remember that in um, your training and your test, you will have the same line. Because whatever you train in the training session, you have all the weightage. That weightage will be used in your testing. So that's why if you do not include enough sample, you will tend to have a high misclassification. So it's good to have more samples in your training so that it will cover most of the area that you have in your sample. So any question on this? Okay, so in summary, what you need to understand is for the perceptron prediction, we are looking at the sign of the computation of the weightage and the input that you have. If it's greater than or equal to 0, they will be positive. And if less than 0, they will be negative. Okay. And you also have to look at the update rule. So this is the basic formula that you have. Okay. And this is your learning rate. And this is your actual output. This is your predicted output. And this is the value of that particular features in that particular sample. So xi refer to instant number, j refer to feature that you have. So for multi-class perceptron, so because if you notice that this is only for binary classification. So if you have multi-class classification, you need to add more. Because the output of this may be 0 or 1. Similar to this, for this class, the output will be, if this is 1, so the rest will be 0. Okay? So if it is 0, this is 1, 0, 0. So basically, you just add the more neuron on the output that you have. Okay. Okay. For this one, let me walk you through this simple example in which we have 4 column of numerical values. So what we want to do is we want to predict the class of that particular sample that we have. So we have 3 classes: Satosa, Versicolor, and Virginica. Okay. So based on the length, the sepal length, and also width, and also the petal length and width, we are trying to classify or learn how to classify the setosa and vesicular genica samples. So the first thing that we are looking here is that we load the data. We are using the iris data, and over here, the second one, we are extracting the first 100 rows. And this is column number 1, 3, and 5. So we are looking at the sepal length, petal length, and also the species. Okay, this is the label, the classes that we try to learn. So we are only looking at the length for the sepal and petal here. So if we try to plot them, so this is what we have. So all the color belong to here, where the petal length and also the sepal length are greater. For short one, for shorter sepal and petal length, we have over here. So definitely from here we can draw a line here. So what we want to learn is we want to learn y, where we have x, a, x1 plus b, x. Don't use the b. B is use that one as the bias. So weightage x1 plus weightage 2 x2 plus bias. So this is your x1, this is your x2. So we want to learn this weightage. Okay, how do we use that one? First, we need to look at the how do we define the Perceptron processing. So remember that we are saying that the function that we have here. Okay, so this is the square root of the sum of the x. Let me see. Okay, so this is basically we are looking at the distance from that particular point to the line that we are looking at here. So for example, we are trying to find the distance between this particular point to the plane that we have. This is the plane that we have. Okay, so the distance would be we just put that particular value inside here, y, then the z, then the distance will be this. Okay, so do we use this one? For example, this is the function that we define. So this is the Euclidean distance. So we use this function to measure the distance between the plane. So this is your b, yes, and this is your w. Wait, yeah. So this one we define the function distance from the plane. We call this one here in which we we put in the x and also the weightage and also the bias here. So we apply the distance between the x to the distant plane. So the distance will be, this is the plane that we are talking about. So we have the weightage and the bias here and also the x here. So x, y, z we have here, and this one will give you negative or positive, that they belong to the lower or the upper side of the line. So this is the function that we use in updating the weightage. So firstly, we initialize the bias to be 0, and then this one trying to on the number of updates of the weightage. And this is the computing the max value between the Euclidean distance norm and also 1 here, okay, for this particular x. So what happened is, while your mark is not complete, as you pause here, so we are trying to classify your wait. So this is when we are looking at the weightage. We want to update the weightage. This is when we update the bias that we have. So basically, this one is, this is your what? This is your output, and this is what? This is your x, and this is your input. So weightage that you have plus the learning rate times the output that you have, because y is basically your output and x is your input that you have. Your learning rate is 1 here. So this is how you update the weight in the B and the K. This is only when you have this is your actual output, this is your predicted output. Okay, so this is your predicted output that you have. When the X, the input, the weightage, and also the bias. So you classify the predicted C, you compare with the actual one. If they are not the same, then you update the W here. Okay. And this one will return the list of weightage that you have, list of bias that you have, and also the how many times you update the weightage that you have. So this function, if you retype in the R environment, it will give you the Perceptron function that will update the weightage. Each item that misclassified by the Perceptron. So once we have this, so we can use this Perceptron. So how do we use the Perceptron here? Okay, over here we are combining the column between the sepal and also the metal here. So this is your X, this is your input, and your Y will be the classes. If they are the same with the Satosa, we put +1. If not the same, we put -1. So remember that Perceptron, we only have binary. So walaupun here we have three classes, yeah. So we are looking at one against the other classes. So give the X, so the X is your sample and Y is your label. Okay, so when they plot this one, they plot the X. The X is basically your sample and petal. Okay, so this is the first column, so this is the second column. Okay, so we should be able to draw a line that separates these two. So when we try to see, okay, this is all the point that positive, they will use the black one. All the point which is the negative, they will plot them as the red one. So you can see two sub group here. One is red and one is the black one. So the function of the perceptron is to estimate the weightage or the slope of the line so that it can draw a line that separates these two groups. Okay. So P is we obtain from the perceptron lah. So this is the perceptron that we have. So this is the model that we learn given the x and the y. As the perceptron function is defined here, right? So we initialize all the weightage based on the comparison of the actual and the predicted output. So we are looking at the B and also the W in order to draw the line. So this is the intercept and this is the slope. This is the weightage for individual item that we have. And this is just drawing the line that we have here. Okay. Okay. So I think this is the last slide. No. Okay. So this is another example that looking at the multi-layer perceptron. So this is the previous example are looking at the binary classification only. So for multi-layer perceptron, they are extremely used for complex problem or if you want to do multi-class classification. Okay, so let's look at this one. We have a few parameter here. X is your input, Y is your corresponding target values or the label. This is the size of your hidden layer, maximum iteration. This is the activation function that you use for all the hidden unit, and this is for the output unit, and this is the matrix with input to test the network, and then this is the corresponding target. So how do we use this MLP function? First, we are looking at the data that we have. We install this RSNNS. So this is where we get the multi-layer perceptron. We get the data from here. This one we are looking at reshuffling the data that we have. So we use sampling, and length will give you number of rows that you have, and this is number of column that you have. And we are separating the input from the label. So remember that we have 5 column here. The last one is the label. So this one we are looking at the fifth column to be put in the label, the target. So the first 4 column indicate the length and the width of the petal and the settle. Okay, and this one is used to split your data into 85% and 50%, and then normalize the value so that you don't have big differences between all the column that you have. Okay, so this is your model, multi-layer perceptron, and all of these are all the function that we have defined just now. So this is your target, this is your input, maximum iteration, this is the learning function parameter. Yeah. This is your learning rate. Okay, this is the size of your neuron, and this is the training. This is the target label. This is your input. So if you look at the summary and also the weight of the model, you have something like this. Okay, so when we try to plot the error that you have, so the number of iteration here, the more iteration you have, it will give you a lower sum square error here. And when you try to use this model is produced when you call the multi-layer perceptron here. So this is your model that you have. You use the model to perform the prediction in order to look at the accuracy here. So you provide the test input data here, and the output of your prediction is here. Then you will plot the regression error against the get test that you have. So here we are looking at the red one. No, yeah. So we have the black one that can split the data of the classes that you have. The red one is the one that you predict should be aligned with the black one. So we can use correlation to measure between the training that you have and what you have in the test. And we can use the confusion matrix function to look at the to compute the accuracy of your multi-layer perceptron. So we are looking at this 2 and 3 here. And also this is during the training, this during the test. So this is okay. And this is the one that error here. We don't count this one because this is considered as between the two classes. So we just ignore that. So when you plot the ROC is used to compare two different models. So you want to maximize the plotting here going to the upper left corner here. So what we can say that this is better than this because this one cover less area under the curve. So this is during the training. This is during the testing. And this is the final one. What we have here is that we have this one. So use this method. The pattern is recognized as classified correctly if the output of exactly one output unit is greater than or equal to h. And the output of all. So this is what we call the default value for I and h. I and h here defined here. Okay. Let me not I and h. This is low and high. So this is low and high. So the output of exactly one output is a unit is greater than or equal to the high threshold here, and the output of all the output unit is lower than the low threshold here. So below 0.4. So if they above 0.6, that means they belong to that particular class. If they below 0.4, meaning that they belong to not belong to the class. Okay, so in this session you are looking at the perceptron. We're looking also at the multi-layer perceptron for the multi-class classification. The most important part that you need to look at here is how the updating process happen in the perceptron, adjusting the weightage so that they can learn the weightage to fit the data that they have. So that is the most important part because you'll be asked in the exam. We'll have a separate session to do this one, multi-layer perceptron, also the perceptron here. So we will go over this one again one more time to make sure you understand what the command means. So I will go through this one again. Okay, so but for the time being, you can go through this practical, but you don't have to submit lah, this one. But I will assign a new practical assignment for you all. But that one, I think we have 2 or 3 practical sessions for you. You need to submit lah. Okay. Any question?